As I said, it doesn't have to be a complicated diagram. Just making sure we're visualizing these. So that's what, 7.3. You notice I'm not putting on a terribly complex scale on this or anything. Just want to make sure we're visualizing what we're doing. So we have expectations. Like this is a lot to this curve, so this is going to be a fairly high probability. And again, we could find, using our tables, we could, and I kind of miss it because I like it, but find our z-score and find the probability that the z-score, oops, sorry. Yeah, sorry, I don't know why I erased that. That the z-score is less than whatever the z-score is that we get for 6.7, and then find the probability that the z-score is less than whatever the z-score is for 3.1. Calculate those two z-scores, subtract those probabilities from the table, and get that probability that we want. And I do suggest that you guys practice doing that by hand some with those tables. But frankly, once we start using the calculator a fair amount, the speed and precision that the calculator allows is going to start getting handier and handier. If we want to go from 3.1 up to 6.7 with a mean of 5.7 and a standard deviation of 1.6, paste, enter, it's going to shoot out a probability. 0.6819. Why not? And it's actually a little smaller than I would have expected, but not unreasonable. Between here and here would have been 64%, or sorry, 68%. So we lost a little bit here, gained a little bit there, and it's still about 68%. Okay, I believe that. I still thought it would have been a little bit bigger, but it's not crazy. But yeah, that's just a normal CDF, lower bound, upper bound, average, mean average specifically, standard deviation, and that's our tool. Questions about that? Are you drawing the diagram? It'll make a difference.
The diagram does help you get an idea if your answer is reasonable.
Well, and that's one of the dangerous things with the calculator. If this had said, 0.418, we'd have, it's really easy to go, okay, that seems reasonable. But with this diagram, like, that seems small. I'm going to go look and make sure, like, what did I type in weird? Did I do something wrong? So even if it's just that expectation, kind of being able to check and make sure that's a reasonable value is helpful. So it really is, it only takes a handful of seconds and it can make a big difference. Let's look at going the other way though. So still we need to be given a data set here. So I'm going to give us a mean and a standard deviation, fairly simple one because it doesn't make that much of a difference really. But instead of finding a proportion given some bounds, it's really common for us to need to go the other way. And one of the common places we see this is in a percentile. So I'm just going to write it that way. So let's say we want to find the 75th percentile. Now, what does that mean? So our mean's still at 10. Our standard deviation is 2, so that's 12, and 8, and so on. The 75th percentile. We hear about percentiles fairly often. We often don't even think about it. But if you're in the 75th percentile, that means you're doing fairly well. If you're in the 90th percentile, you're up there with the good values. If you're in the 99th percentiles, good or bad, you're in the big values. So 75th percentile means that 75% of the data is lower than that percentile value. So this value here, if the area or proportion below is 0.75, then this location, this X value, is the 75th percentile. 75th percentile. And percentiles are common ways to, to measure data. Like, particularly if you have a child, they'll measure its, height, weight, length, head circumference, all that kind of stuff, and tell you what those percentiles are. If you're trying to get into a school program, they'll say, we accept people who score on this test in the 80th percentile, or kids graduating or people graduating through this program get in the 90th percentile of salaries in the chosen field. So we hear percentile data fairly often out there in the world. So if we're told, for whatever this data set is, we want to or told that we're in that 75th percentile, and we want to know what that value is, it's essentially the same questions that we've been doing, but backwards. We're being given the proportion as opposed to asked for the proportion. So again, if we want to use the table, we certainly could. On the table, we'd have to find 0.7500 as an area. So we'd have to reverse our logic. So if we go to the table, and we'll talk about how to do this with the calculator in a minute. On this table, we want to find that 75.7500 area or proportion or percent, whatever you want to call it, or as close as we can get. So let me get this stuff out of the way. So let's see, there's 0.7422, 7454, 7486, 7517. So we passed it. So it's going to be one of those two. And we just want to pick the one that's closest to get as good an approximation as we can. So 7486, that is, say it up here, that is less by 14. 7517 is more by 17 than what we want. So the 7486 is closer. So this is going to associate with a z-score of 0.67. Coincidentally, the one we were working with before. So instead of going from a z-score to a proportion, we're going from that proportion, or as close as we can get to it, to a z-score. So we need a z of 0.67. Okay, given a z-score, we should be able to find our value. Got to go from a z-score to a value with our equation for z-scores. We know z's are equal to the value minus the mean over the standard deviation. So if our z-score is 0.67 and our mean was 10 and our standard deviation was 2, we should be able to solve for that x. So multiply by 2, multiply by 2. So that's what, 1.34, correct me if I'm wrong with that, equals x minus 10. Add the 10, 11.34. So that's our value. So if our average is 10 and our standard deviation is 2, well, let me change that. A value of 11.34 makes the 75th percentile. That takes a little practice.
So Matt, in your drawing,
Yeah.
you were thinking that 75th percentile was more than one z-score away, and it's a little less, right?
Yep.
That's just because you're just approximating it'd be somewhere around there?
Yep.
Okay. Is that usually the case? Like 0.75 is like usually a little less than one?
Yes, it is actually.
Okay.
And actually, it always is, because it always makes that that z.
What percentile is usually one z-score?
Well, it does vary actually. Yeah.
Okay.
And actually, an interesting point, we actually have a name for the 75th percentile. That was our Q3. Remember that?
Yeah.
So if we wanted Q1 is our 25th percentile. So sometimes we will be asked stuff like that, but we'll play with that more in a bit. Now, this is doing this by hand. Certainly you're waiting to see, well, what's the calculator way? Because that's probably faster, right? And you're right, it is. But I, again, want to encourage you to do some of these this way to kind of practice the logic of what's happening here. Because as we go to the calculator and start asking the calculator how to do this problem, you're going to see really fast. It allows you to not have to know too much about what you're doing, as long as you know what to type in, and we got to know what to type in. So how do we go backwards with these? Well, we use the inverse normal. So in our calculator, we have INV normal. That's our inverse normal. So if we go to the inverse normal, it'll ask for the area we want. Again, that's the proportion. That's the probability. So that's our 0.7500. And you don't actually have to put the zeros. I'm just in that habit. Should take them off because you don't need them. Our average, our mean was what, 10? Our standard deviation was 2. Paste it, calculate it, 11.34. Now this would be rounded to 11.35. So those are a little bit different. Again, did we expect them to be exactly the same? Remember back here when we had to pick, it's between these two? That means we're approximating a bit. So actually, I'm surprised this is as close as it is. Because it's, you know, the 4.8 we'd have rounded up. So the fact that this was missing a little tiny piece makes sense because we were missing that little tiny piece of area when we rounded down. So again, nice part about the calculator is you can bust these out very, very quickly. The dangerous thing with the calculator is because of that, it's easy to lose sight of what it is you are doing. So try to focus on that. Questions on any of that so far? You guys got quiet today. And then somebody left. So let's look at an application question. Read that question and try to decide how you'd approach it using these tools. Now, in this section, we're talking about normal distribution. So we can feel pretty confident that we're dealing with a normal distribution problem. As we get into chapters 8, 9, and 10, particularly 8 and 9, one of the first things we're going to have to decide is, are we in a normally distributed problem or are we in a binomial distributed problem? We have to identify the type of problem we're working with. But, given a mean and a standard deviation, we're in a distributed data problem, and we're in that section, so that's not as much of a concern. Once we've identified that this is a normally distributed data problem, we have to identify what direction we're going. Are we up here and we're going from data values and outputting proportions like we did in these first couple, or are we in this mode where we've been given an area, given a proportion, and asked for values? So it's really important to start that with these problems. It's the first thing you ask yourself. Read the question, make sure you understand what it's asking, try to draw a diagram, and identify, have we been given values for our data, or have we been given a proportion for our data? Now, we have to be given our descriptive statistics, our mean and standard deviation. Those don't count as values. They're not values of particular fruits. So have we, in this problem, and I want you to respond in the chat or with your mics, have we been given values and asked for a proportion, or have we been given a proportion and we're being asked for values? Given values should be an or, sorry. Have we been given values or have we been given a proportion?
Given a proportion, asking for a value.
They gave us this 2% of. We're asked for how many grams. We're asked for a value of weight in grams, given that that proportion of fruit above that will be 2%. So here we've been given a proportion. If we're given a proportion, we will be using that inverse tool to find values. If we're given values, we will use the norm PDF or the z-score tables like we have been to find that proportion. So if we're given values and need proportions, norm, oops, sorry, not PDF, CDF. That's me, norm, CDF. If we're given the proportions and want values, that's our norm inverse tool. What proportion have we been given here that we're going to use? If we go to our distribution tool and our inverse normal, it asks for an area. What area are we going to put in here? Somebody other than Kim, what area are we going to put in there?
Wouldn't it be the 426 grams?
Is the 426 grams a percentage, a probability? Because remember, these areas are proportions. So when it asks for area there, think of area as a proportion, or if you prefer, a probability. That grams is a weight, it's an amount, it's a value. The probability that we're told is that 2%, right? But is that what we're going to put into the tool? This is where these questions can go a bit awry. Well, up here, we put in the 0.75. The problem asked for the 75th percentile. So it asked for where is it 75%. So we put in the 75%. But it wanted 75% and down. That's what our tool naturally wants to give us. So if we want the heaviest 2%, that's some value and upward. Our tool doesn't want to do that. So if we want this value, we've got to ask it the 98%. Fair? The highest 2%, the boundary for the highest 2% is the same as the boundary for the lowest 98%, and that's what our tool does. I mentioned this last week a bunch, that our tools will naturally want to measure things down, not up. So the area that we'd want is the 0.98 with our standard deviation of 426. You're right, Andrea, we do need to tell it that. And the 33.
Also, if you draw that picture, then you can see that if you try to put in 0.02, it's not even going to be near there.
Oh yeah, you'll get some tiny value down here. It'll be like, 398. And you'll go, wait, how is that the largest 2%?
Yeah.
That's less than the mean. So yeah, those diagrams help with that expectation. So I'm going to paste that, evaluate it, 493. And again, we always want to ask ourselves, as Kim is saying, is that 493, or I'm going to say 494 grams? Is that value reasonable in this question? Well, averaging 426, standard deviation of 33. So a couple standard deviations up for the highest 2%, that should seem reasonable. Cool. These do take practice. Please, please, please draw the diagrams when you do it. It does make a big difference in the long run, particularly with what we're going to add on top of it in chapter 8. Now, this is the last section in our chapter 6, chapter 7 material. You do have a test, tomorrow afternoon, I think it is? Or you can take it in the morning, but we're going to do review tomorrow. So you'll probably take it after class. There's really not, we're going to add stuff on top of this, but there's really not much more to this other than making sure you get that practice in. Fair? So go get that practice. Bring good questions tomorrow and draw those diagrams. Anything I can help you with before you run off today?
Nope, thanks. Bye.
Andrea, Ally, you two good?
I was having a problem I think I've tried this problem 20 times and I could not figure it out. It was, now if I can't find it, it was basically just asking to find the z-score of the shaded area, and no matter what I attempted, it was not correct.
Okay, so we would need a shaded area. So, and usually it says things like, Z less than C and find C, right?
All it said was just, it gave me the shaded area that's like 0.44 and find.
Okay.
4.
Was the shaded area the upper shaded, the upper area, or the bottom area?
It was upper.
Upper, okay, that's what I figured. Let me grab one of those. It won't be the same numbers, obviously, but. Oops. So like that?
Yes.
Okay. I always like how it has this little, you can zoom in on it. There's nothing about this question that zooming in is helpful for. But this is actually a lot like the problem we just looked at.
Okay.
The shaded area, I'm not sure I'm happy with this diagram as much because that area looks kind of big, but we'll see when we find that those, numbers. It doesn't have to be to scale, right?
Mhm.
So if the shaded area we want is this upper section, does our tool like finding upper sections? Or does it like finding lower sections?
Lower. On the calculator, it'd be lower.
Or on the table, lower?
Oh.
All of our tools really are more associated with lower sections. The normal PDF is about the only one that's not, and it defaults actually to lower. It puts in that -1 E99 to default to lower,
Right.
but we can adjust that. All of our other tools, they don't even allow us to adjust it. So what would that lower area be?
Wouldn't you have to subtract it? Like the 1 subtract?
Yep. And what's that subtracted from 1?
Wait, hold on a second.
Don't get dependent on that calculator. Fair?
I was putting that in and it was still like wrong.
Well, that's okay. We're not done yet. Let's see where it
Oh,
ends
okay.
up. So that's the area, right,
Right.
that we're going to be looking for, but we still need that z-score. Fair?
Right. Okay.
So if we want to do this, which do you want to do it with? The table, the calculator, or both?
I was trying to do it with the table, but now I kind of understand with the calculator a little bit more.
Well, let's do both.
Okay.
So we'd want 0.93, as close as we can get to 0.93.
Without going over, or I guess
You can go over, just as close as you can get.
Gotcha.
So 0.92, 0.927, 0.92. So it's going to be one of these two, whichever is closest. So this one is off by 8. This one's off by 6. So I'd use this one.
Right.
So that's 1.48. So 1.48. So I'm going to bring that 1.48 back here. So that z-score is 1.48. And actually, it didn't, that's all it wanted was the z-score associated with that area. So technically, that's done.
Oh, okay.
If it wanted the value, then we'd have to know what the mean and standard deviation was, and we could compute it into a value. But from a, if it just asks for the z-score, that's all we can tell it.
Okay.
Now, if we wanted to do that with our calculator, we would go to our, which one? Our norms EDF or I'm inverse.
Wouldn't it be inverse?
It would be inverse, good, because we're going through from a proportion to a value. We'd be putting in that lower region because that's what our tool does. What would our mean be?
Wouldn't it be the 1.48?
No. That's the z-score. That's what we're hoping this thing outputs.
Oh, that's okay. Or shoot. Because we have,
when we're standardized, what's our mean?
it's 0.
It's 0.
Oh. 0.
What's our standard deviation?
Would it be the 0.07? Oh, it's 1. I'm mixing all of this up.
Well, that is weird though, because that what the standardization does is it turns everything into z-scores, right?
Right.
And remember, z-scores tell us how far or how many standard deviations we are from the mean.
Okay.
So how far is the mean from itself? 0 from itself. So the mean becomes 0.
Okay.
How many standard deviations away from the mean is the first standard deviation away from the mean? It is 1 standard deviation away from the mean. That's a weird thing to say, though. Even that sentence, how many standard deviations from the mean is 1 standard deviation from the mean? Well, it's 1 standard deviation from the mean, Matt. But it makes it a weird thing to, to express. So people often want to find other things for it to be.
Okay.
But in our standardized curve, in our distribution of z-scores, our mean is always 0 and our standard deviation is always 1.
Okay. 1 point.
And paste that. Enter. It should match what we had.
Yeah.
Oh, and it does even round to it. That's nice. And if it was off a tiny bit, then okay, fine. It's off a tiny bit because our table is an approximative tool. But that one actually worked out nice.
All right. Well, you cleared up what I was doing wrong. So
Cool.
Thank you.
Nick, Tessa, how about you two? You guys good? Got any questions? Good for now. Awesome. Is that yes, you had some questions, or yes, you're good for now? The exclamation point sounds more like a yep, I'm good. But if anything comes up, let me know. And good. And do make sure you work on as much as you can tonight so you can come in tomorrow with good questions. Okay? And I'll see you then. Have a wonderful day.